What is up, car and tech fans? Welcome back to another garage tinkering video where today we're going to delve into the world of CANBus bridging, or creating a man in the middle. So I'm going to show you what one is, then we'll talk about why you would do it, and then we'll look at how you do it. So I'll share the code and everything for this demonstration if you want to grab it all in advance. Links to the GitHub are down below. So if you've never come across the term CANBus bridging or man in the middle, what do you need to fundamentally know? What is it? What we're doing very broadly is we're just going to create a device on an ESP32 that listens to a CANBus, in this case the car's CANBus, but then replicates the signal from that CANBus onto a second private CANBus. And it's on that second small private CANBus that we're going to be attaching all of the gauges and other inputs and outputs that we create as part of this ongoing car hacking series, rather than putting them directly onto the CANBus of the car. There are several reasons why you might want to do this, but perhaps the biggest one is that some cars don't like it when you start sending CANBus information back to it from a source that it didn't expect. Depending on your car, depends how it reacts when you send information back to it. Obviously, when we're doing CANBus sniffing, we're just listening to passive data. It's traveling back and forth around the car and through the various CANBuses, and we're just listening to it and extracting the little bits of information that we want. But if we start injecting more stuff into there, the ECU can do one of several things. Some cars don't care. They go, oh, we've got all this extra space on the CANBus. We're not maxing out on our bits per second. We'll just allow this data to pass through. Some of them will look at the information that's coming in and say, oh, that's an invalid ID, or that ID has come from a place where I didn't expect it. I was expecting the window down signal to come from the body control module, not from the OBD2. So it just filters and rejects it. But you do get some where the ECU really doesn't like it if you start sending it things that it didn't expect, and it can cause corruption or invalid signals to be sent out by the ECU, which can cause loads of issues, both electrical and mechanical, around the car. And in the worst case, you could completely brick your ECU. It doesn't happen very often, and they're generally protected against it now, but there are cars where that will happen. Unfortunately, I don't have an extensive list of how every different car type reacts. I know the 350Z kind of goes, oh yeah, we've got some space here. Go ahead, stick some stuff on there. But I'm still taking precautions and making a separate second little network. And because I'm doing that, it means I have complete control of all of the data that is going on inside that network. And I can use my CAN bridge, or my man in the middle, to do a number of things which makes the life of all of my other components, like my gauges, much, much easier. So I'm going to walk you through a demo, starting with a very simple CAN sender and CAN receiver, and then we'll build a man in the middle on top of it, and I'll show you some of the reasons I think it's a really cool thing to do and why I am going to recommend it if you want to use gauges like this. This is a very simple CANBus network. We're using two of my ultimate gauge boards, and because these have got CAN transceivers built into them already, we can literally just take the wires out of the JST, connect them up, and we're ready to send CANBus data. The CAN high and the CAN low have both been put into the same rows here, so they're sending data to one another, and we put both of the grounds into a common ground plane because sometimes it complains if you don't. The 5-volt input signals are just tucked away at the side. Because we've got these plugged into the USB right now, they're not required. And for this simulation, we need to imagine that the one on the left here is the car, and it's distributing its CANBus signals, and the one on the right is one of our devices, and it's just listening to all those CAN signals. What am I actually sending, though? Because I don't have all the car signal stuff here. So what I'm actually sending, we can see on these two serials at the bottom here. This one on the left is the sender. This one on the right is the receiver. And all the sender is doing is once every second, it is generating a new 4 byte of data, and then it's stepping one number at a time between ID 100 and ID 109, and then looping back to 100 and counting through again. So it's just simulating A very slow running CAN bus. Like I say, this is one signal every second. The reality of your CAN is it's probably doing somewhere between 500 and 2,000 signals a second. It's much quicker. But if we send that many right now, we're not able to see what's going on. The important thing that we can note here is that the message sent and the message received, basically it's exactly the same time because CAN is incredibly quick, are being shown on both sides of this serial print. And the code is very, very simple. This one is just setting up the GPIO. You'll see TWAI, two-wire automotive interface. That's just the expressive naming convention for CAN. And we've just set up the input-output. We've set up the rate at 500 kilobits, which is what my car uses and what probably most of your car uses. A couple of initializations, then a loop that just goes through and gets each one of the IDs in order and then just loops back through. Generation of random IDs for the bytes, and then it sends that message, and it does that in the loop once every 1 second. Not the most ideal way of simulating a CAN, but it's perfectly fine for this example. The receiver is very, very similar. It's all of the same code, except it has no sending part in it. Instead, this loop is listening out for the message, and if it doesn't find anything within 3 seconds, it says that there's no message received. Otherwise, it prints whatever is coming in on the CAN bus. And you can see, like I say, these are in sync. The best way to do this as we go through is generally focus on the last 2 digits of any one line, and you'll be able to see that they're the same. So this is a normal CANBus interface. If your car was sticking out this information on the left and your gauge was receiving this and then filtering it out to get the information that it wanted, that would work. But maybe we want to do something to this information, or we want to add more things. Let's say we've got an external sensor of some description that's not OEM. For my 350Z, I need to put a oil temperature sensor into the car. It doesn't exist OEM. So I'm going to need to get that information into the CANBus. Now, if I was to add a third device to this CANBus and that had an ADC sensor on it, on an ESP32 that listened to that oil temperature sensor and then spat that information out into the CANBus, into this CANBus, in a way that I knew that I wanted to receive it for my gauge. So I give it an ID that I want, and then I give it the values in a format that I want. That might work fine, and the car might just ignore it or just let it pass through. But the car might go, what's this? I don't know what this is, and freak out. That's where our man in the middle comes in. So we're going to change the network slightly and put another device in the middle, and then we'll have a look at how we change the code. We'll start by just breaking this CANBus network and separating the CAN high and the CAN low from the car, the sender, and our receiver. And then we bring in the board that we're going to use to actually create our man in the middle, this ESP32-P4 from Waveshare. It's their dev kit board and basically the flagship of the ESP32 system. It is the tippity top of the mountain of what you can get for this particular ecosystem right now. And the reason we're going to use this is because it has 3 individual TWAI controllers, which means we can connect 3 different CAN buses up, and it can allow it to receive and transmit on all of them independently. Now, if you can't get hold of an ESP32-P4, which is probably the case, you can also do this on an ESP32C6, which has 2 TWAI interfaces on it. So if you want to do all of this on one device, C6 or P4, they're basically your only options if you're doing this with an ESP32. Unlike my boards, though, these don't have built-in CANBus transceivers. And because they don't have a CAN transceiver, we're going to have to use one. I have these. These are the TJA1051 CAN transceivers, high speed, low power consumption, do up to 1 megabit a second. So they'll do exactly what we need for this network. So we're going to connect the CAN high and the CAN low from the sender, from the car, to the CAN high and CAN low of the transceiver on one side of this network, and then connect the RX and the TX to a couple of the GPIO pins. In this case, we're picking 22 and 21 for the RX and TX respectively. And then do exactly the same on the other side of the network. Connect the CAN high and the CAN low to the CAN high, CAN low of the transceiver. Connect the RX and the TX to the GPIOs. Again, we'll pick 47 for the RX and 27 for the TX. And then I need to power these two boards. We could do it just from like the 5-volt output of any one of these boards. But instead, just to keep things nice and groovy, I'm going to use an independent power supply. This is a 12-volt to 5-volt regulator module. Be absolutely perfect. So I'm just going to make the bottom rail along here have the power and the ground come from that, and then power the two transceivers from that rail. All pretty simple. The setup for this isn't too difficult, but effectively, if you imagine splitting this whole circuit in half, we've got CANBus on one side, which is the car's CANBus, which is coming into the ESP32-P4. And then on the right-hand side, we have our private CANBus that has nothing to do. It's not connected really in any way to the car's CAN. It's completely private. When we go back to looking at our code, we'll see that the sent on the left and the received on the final one on the right-hand side are still completely in sync. Now, there is something here that I should make note of because you might see it. I've negated to put any 120 ohm resistors in this circuit. I should definitely have them on both sides of the network because I have terminated the CANBus on both sides of the network. But sometimes you can get away with it. We might experience some packet loss and some data corruption because I haven't done that. In actual car, we definitely use the CANBus terminating resistors when we need them. More on that at a later date. Like there, you can see I've just lost a few packets. It'll happen. Generally speaking, once we've got our resistors in place, that won't happen anymore. So I guess the important thing is to look at this extra piece. So this is the VS code that has got all the code on it for the P4. It's in VS code compared to the other, which is in Arduino IDE. These are running off my Arduino IDE setup for my own boards, whereas the P4s right now run best off ESP IDF. So they're just using different setups, but the code is very, very similar between the two. In fact, it's almost identical. So what we're seeing here is the sender on the left-hand side send the information out on its CANBus, and this man in the middle, the P4, is getting that information in, and then it's just immediately forwarding it on to the second CANBus. So it's just forwarding that message. And as we can see, all three of these are currently completely in line. And if we just take a look at the code, very, very similar to what we did on these ones. But because we're doing it on a man in the middle or a bridged approach, we need to use the TJA1051 V2, which allows us to set up handles for 2, or in this case, 3 different CANBus networks. So they're just, instead of initializing the one like we did over here, we initialize 2 different ones and we start them independently. And all we're going to do is check for new information coming in like we were doing. And as soon as something new arrives, that message then just gets forwarded onto the second CANBus. Very, very simple. It's just taking it in, forwarding it straight on. So why is that a good thing? Why was that worth doing? Let's say I want to inject more information into the CANBus. It could be a sensor or a button press or anything like that. So let's just add something to the circuit to simulate that. And we'll do a simple one. We'll just do a button press. So we'll just grab ourselves a momentary switch and stick it over here on this side of the board, and then connect it up with a couple of DuPont cables to the ground and a GPIO pin of choice. It doesn't really matter which one. We're going to pick ID number 4, and that's a button wired up, which obviously right now does absolutely nothing. If I add in some simple code, which I'll admit I've already written, just drop that in like so. Now what's going to happen is when I press that button, it'll sense it and it's going to create a new CANBus message with the button press, which has the ID of 200 and the data is just 4 255 packets, so 2 FF packets, and it's going to inject that out as and when we press the button. So let's just see what happens when that happens. I need to turn all these back on. There we go, it's all back up and running again. So as you can see, ticking along exactly as it was. Now let's push the button. There we go. You can see on the right hand side there, 200 has been injected out onto the network, but it's not on the left hand side. It's just button pressed has been sent, and it's just sent it to our micro CAN. It's not sent it to the car's CANBus, which means I can now add extra information into my own little private CANBus, and I can control it, and I know that that's not going to have any negative effect on the car. Because I control the network and I know what IDs are being used on it, only the ones that either I've seen come in from the car or that I've allocated, then it's a lot safer and there's a lot less chance of something going wrong or damaging it. And I can effectively have as many of these external inputs that I want, either directly on the man in the middle like this, or on other devices that are on that private CANBus. They could be buttons, they could be sensors, it could be information that comes in from a web application that you build on an ESP32. It could be any source of data, but it's now being controlled by us. But that's only one benefit of doing this. There are other ones. For example, stress relief, for want of a better term. If you were to connect one of these gauges directly to your car's CANBus and you want it to display, say, two of your values, maybe let's say RPM and speed, there are hundreds and hundreds and hundreds of bits of information that are coming in every single second, and it's going to need to filter through that other information, find the stuff that it wants, and use that to update LVGL or whatever graphics suite you might be using. The combination of having to filter through all this information and update LVGL, which is notoriously system intensive anyway, can put a lot of strain onto your ESP. So we're better to reduce the noise and reduce the amount of traffic that is on our micro CANBus to just the information that we require. So if we know that maybe all of the information that is coming in is there's 50 IDs and we only need 5 of them, we can use our man in the middle to strip away all of the extra noise that we don't require, so that the CANBus information that we are listening to is relevant with information that we have. So in this example, we currently have identifiers coming in and then we're just re-forwarding them on, and they have IDs from 100 through to 109. So we can say, all right, we don't need any of the IDs that are greater than 106. So let's strip all of them out. And we can just, around this transmit, put a filter, which would be really, really easy, with like, if the message.identifier, as it's called in this instance, is less than or equal to 105, then do all of this. And if it's not, then don't do all of that. So that's just going to create a really simple, when that's actually correctly in equals, filter that gets rid of half of the information here that we don't need to use. So here it goes. 1, 2, 3, 4, 5, 6, 7 is all coming in, but it's not being forwarded. We're only forwarding 0, 1, 2, 3, 4, 5. We've got a little bit of packet loss there, but as I said, that's expected given we've not set this up properly. But for the most part, we're getting 0, 1, 2, 3, 4, 5, and we're filtering out 6, 7, 8, and 9 because we don't need that information on our CANBus. So we've just effectively reduced the amount of data that the ESP has to filter at the endpoint by around 50%. So if we can do that in the car and we can identify the IDs, you wouldn't necessarily just have a less than or equal to like we've done here. We might have a filter list and we just match the ones on that filter list and just only send through the ones that we want. It means we can keep the information on our micro CAN tight and necessary, and it only has information on it that we actually need. Also, we can manipulate the data. So again, when we're at the top of here, we could say, let's do the message identifier again here. If the message identifier is equal to, let's go for the first one, 100, then the message dot data in position 0 is equal to 0. And we'll do 2 of those. So we'll do that. And then on 2, The one in the third version, so the final spot, is FF. So what we're trying to do here is manipulate data and potentially prepare it for what it needs to be at the endpoint when it's being ingested. So, right, let's just take a look. So we should have forwarding message. There you go. So 0, 0. Well, at 100, the first bit of data is 0. And at 102, the last bit of data is FF. And you can see that's the same all the time. So we've manipulated that little bit of data and changed it to what we want to do. There are a number of reasons you might want to do this. For example, you might want to use this to set flags for something in a byte of data that's not otherwise used in an ID. You might want to use it to artificially increase a value. So maybe it has an offset for some reason, and maybe you want to add an amount to it or minus an amount to it to create that offset, so you don't then have to do that on the gauge. You don't have to apply the offsets. Or maybe you want to simplify things further and bunch information together. We could make a single ID that had 8 data points on it, and we extract all the data points that we want from the incoming data, amalgamate them together, and create a single CANBus ID that has all of the information in it that one of our gauges requires. Then it's just very simply processing that one piece of data and updating all of the values accordingly. That gives us better control of refresh rates and how fast data is being sent at the gauges themselves, rather than the car having any say in that. There are a lot of benefits of doing it this way, but the big ones being, like I've said, we secure our car's network, we don't risk injecting any bad information onto it, and we have the ability to filter and manipulate data before it's even sent to the gauges and reduce the stress load on them so that they can be allowed to just do what they need to do, which is create fluid, good-looking gauges and not have to put loads of system resource into filtering and manipulating data. Keeps it very, very simple. It also means that when we're connecting all of our network of devices up, whether, like I say, they be sensors or buttons or phone controls, we've got a defined standard of how we send data. It's the standard CANBus way. We don't have to worry about the structure type that we might be setting up to use ESP-NOW to do all of this wirelessly, because all of the definitions and the standards of how CANBus data is designed and sent already exists. We're just piggybacking on the back of it, which means it becomes relatively universal. So if everybody was to design all of their additional things for these networks using this standard, all of the devices that you guys are interested in making for this suite will be plug and play and work with most cars. So long as we, try and identify IDs that are not generally used, which are often the higher numbers, it should generally work pretty well. So this was a little look at, man in the middle or CANBus Bridges. They're both the same thing, really. Hopefully you've got an understanding of why it's a good thing to do. And it is definitely something I am going to recommend if you are building this suite of gauges out. But if you want to go wirelessly and you're using the Mr. DIY CANBus sniffer, you're already doing this. That is effectively a man in the middle. You're just creating a wireless man in the middle that converts CAN data. Instead of to another CAN network, you're converting it to a ESP-NOW network. It's the same thing, just a different flavor. But doing it this way makes a lot of sense to me. Do you ever want to send information to your car? Yes. I want remote control of certain things in my car, and it is cunning. We're going to look at how you can relatively safely start injecting information into your car and actually have it do things. Like if you want to wind down your windows from your phone. We can do that, and we're going to get there, but safety first, one thing at a time. I expect 95+% of you who are interested in building gauges like this literally just want to listen to your car and update them, and then maybe add a little input here and there. This is, I think, the best way to do that. If you have any questions about all of this, please do let me know in the comments, and be interesting to hear what you think about it. Is it something you want to build? Like I said, the code for this is in a GitHub repo. It's very simple. There's just a sender, a receiver, and a man in the middle bit of code. It's this exact code that you can see on my screen now. It's not done with any plugins or anything. It's just all native TWAI. So everyone should be able to get that running relatively simply, I think. And like I said, if you haven't managed to get access to a P4, you can do this on an ESP32-C6. There are links to get both of those component types. This P4 that I use, the WaveShare dev board, and just a generic C6. There are some links to get those in the description. If you do enjoy this kind of like technical content and you want to see more of it, do let me know, and make sure you hit the subscribe button. I'm waiting to get this space filled with my 100,000 subscriber plaque. I'm quarter of the way there. Come on, people. We can do it. You've all got 3 friends, right? That's enough. Anyway, I hope that something good happens to you today. Have a wicked one. I'll see you in the next video. Take it easy, peeps. Bye-bye.